Chapter 17 in our book deals with electrochemistry, and this is going to discuss wet cells. Electrochemistry is concerned with the conversion between chemical and electrical energy. A galvanic cell or voltaic cell is spontaneous, and a battery is an example, and it generates electrical current. An electrolytic cell is non-spontaneous and requires electrical current to force it to run. A galvanic cell, being spontaneous, has an E0 or a voltage that's positive. It has a delta G that's negative and a very large KEQ. The reaction is driven to the right. Whereas an electrolytic cell is an uphill reaction. It has a negative voltage. It's non-spontaneous. Its delta G is positive and its KEQ is very small. Here's an example of a redox reaction between zinc metal and copper ions producing zinc ions and copper metal. Pause video, identify the oxidation half reaction and the reduction half reaction. Remember to include electrons. Here's the oxidation reaction showing zinc losing 2 electrons. Here's the reduction reaction showing the copper ions gaining 2 electrons. Turns out that the zinc losing 2 electrons creates a voltage of 0.76 volts, or a cell potential of 0.76 volts. This is spontaneous and is driven naturally to occur. Copper gaining 2 electrons is also a spontaneous reaction that generates 0.34 volts for that half cell. Putting them together, we get an overall cell potential of 1.10 volts, and you simply add the two half reactions to get the whole reaction, add the cell potentials of the voltages to get the overall voltage. Electromotive force, or EMF, is the force or electrical potential that pushes those negatively charged electrons away from the anode and towards the cathode, as we'll see in wet cells coming up. It's also called cell potential, capital E, and typically capital E0 for standard state, or cell voltage. Here's an example of a typical wet cell for our reaction between zinc and copper ions. This reaction does occur spontaneously, but the two are separated from one another. So for example, our copper is on the left as copper plus 2 ions in a solution with sulfate, and sitting in that solution is a strip of copper serving as our electrode. So solid copper in a copper solution, and on the right we have our solid piece of zinc sitting in a zinc sulfate solution. It turns out our sulfate in our copper solution and our sulfate in our zinc solution is simply a spectator ion that needs to be present. Notice we also have this device here in the middle called a salt bridge that holds ions, in this case sodium ions and sulfate ions, and it simply connects the two half cells, the copper cell on the left and the zinc cell on the right. Notice also that between the two electrodes, the zinc electrode and the copper electrode, there's a wire, and in between is a light that'll light up. Turns out that electrons leave the zinc metal, they pass through the wire and come over to this electrode, and the electrons hit the copper 2+ ions, converting them into elemental copper. So if we think of the reaction as having zinc losing 2 electrons and giving them to copper, this would happen if the zinc and the copper were put together in solution, or if they're separated like this, it'll happen as long as this device is set up as shown. So again, the zinc loses electrons, it sends them through the wire over to the copper ions, which are down in this solution. Copper ions come up to the electrode, accept the 2 electrons, and then deposit out as solid copper on this electrode. During the process, zinc is actually going away. It's no longer zinc metal, it's turning into zinc ions. That's one of the products. So we get more zinc ion on the right as it loses electrons. Now this buildup of charge over here couldn't exist for long, as we had a dumping of zinc ions into the right. That would cause a problem, too many positives. So that's what the salt bridge does. It has sodium ions that can run or move over to the left away from this influx of zinc ions into the right beaker. Similarly, if we look into the left beaker, copper is leaving. Copper ions are leaving solution. So there's a deficit of positive charge on the left as copper deposits out as elemental copper. Well, that also causes a problem, and hence the sodiums can run over in the salt bridge and help solve that problem. Now, sodiums moving to the left in the salt bridge correlate with sulfates moving to the right. And again, that helps because on the right we have an excess of zinc ions forming, and the negatives coming in help with that process. And similarly, on the left-hand side, we have a deficit of copper ions, so the sodium comes in to help with that process. So this is an entire wet cell. It requires electrodes. If the circuit is broken, if the wire breaks, or there's a switch, it stops the circuit. If the salt bridge is taken out, we'll ask that in a slide coming up. The anode is the electrode where oxidation occurs. Some people remember that by anode as a vowel and oxidation as a vowel. Some others remember that O in anode and oxidation. Anode, the electrode where oxidation occurs. It's the electrode where electrons are produced. The word comes from it's what anions migrate towards. Anions migrate towards the anode, and it has a negative charge. If we go back one slide, notice that the anode over here has a negative charge shown. The cathode, which we'll show next, has a positive charge. The cathode is the electrode where reduction occurs. So for some folks, cathode starts with a consonant and reduction starts with a consonant, and that's how they remember that. It's the electrode where electrons are consumed. It's where cations migrate towards, hence cathode, cations, and it is assigned a positive charge. Why do electrons flow through the wire to the left as shown? Remember, it's zinc that's donating electrons in this reaction, and it's donating them to copper, so it's the zinc that's giving up electrons, and the electrons have to flow away from the zinc, the anode, and towards the copper, the cathode. What should happen to the mass of the electrodes as time passes? Pause the video and think about that. Well, look at the reaction. Zinc is a reactant and is actually consumed and used up and is going away and turning into zinc ions. So the zinc anode is actually losing mass during this process. Similarly, copper ions are depositing out on the copper electrode or the cathode, so it actually gains mass during the process. So the answer is zinc is losing mass, copper is gaining mass. You may ask yourself if the mass lost by the zinc is equal to the mass lost by the copper. Interesting question I won't answer right now. What if the salt bridge were removed? If the salt bridge were removed, the reaction stops immediately. Though the zinc still wants to donate electrons over the copper ions, that buildup of charge would be too great and the reaction stops immediately. So without the salt bridge, the reaction stops. What should happen to the color of the solution on the left as time passes? We'll pause the video, but remember copper plus 2 has a color, the blue solution shown there. Think about that before advancing video. As time passes, given that copper ions are being lost from the solution on the left and that they have a color, this solution goes from blue to lighter and lighter and lighter blue as the reaction proceeds. Now the reaction on right is shown to have a color, but it actually doesn't. Zinc is a colorless ion and sulfate is a colorless ion, so this is only done for clarity. Why are sulfate ions present in the solutions? They are only spectator ions. What's the point? You can't go and get a jar of copper ions. You can't go and get a jar of zinc ions. So you add copper sulfate, and typically it's a 1 molar solution, and you add zinc sulfate to have for this electrode, for this solution over here. What will happen to the cell potential or voltage as the reaction continues to run? Turns out the voltage will slowly drop. As the reaction proceeds, the concentration of the zinc ion here begins to increase, the concentration of the copper ion begins to decrease, and this is kind of like a battery. Over time it will run down, or this is an example of a battery, and over time it will run down, and the voltage will slowly decrease. For this one, we're not measuring voltage, but our light would get dimmer and dimmer as time goes on. So here's another reaction. Here we have hydrogen gas reacting with copper ions, making copper metal and 2 hydrogen ions. Pause video. What's the oxidation half reaction? What's the reduction half reaction? Here are our 2 answers. Hydrogen is donating 2 electrons to turn into 2 hydrogen ions during our oxidation. Our copper ion is getting reduced to elemental copper as it gains 2 electrons in the reduction reaction. If we look up voltages, it turns out hydrogen turning into hydrogen ion, by definition, hydrogen has a 0 voltage. Copper gaining 2 electrons, this reduction reaction has a 0.34 volt for that cell. Overall, if we add the 0 and the 0.34, we get the overall voltage of 0.34 volts. Is this reaction spontaneous? Yes, because of the positive voltage. Here's a wet cell showing this reaction. Notice on the left we have to have copper as an electrode and copper ions present in a 1 molar solution. We need our salt bridge. We have our wire set up, this time going through a voltmeter. Notice the right-hand reaction is very different though. We have a 1 molar solution of nitric acid, H plus and NO3 minus. The H plus is, even though it's a product, needs to be present at the beginning. Notice we have a standard hydrogen electrode called a SHE, S-H-E, and hydrogen gas is pumped in at a pressure of 1 atmosphere and bubbles of hydrogen form, and that acts as our reactant here. And there's a platinum electrode where the reaction can take place. Electrons can flow through the wire. Again, the hydrogen is losing electrons, and so that's why electrons are leaving it, and copper ions are gaining electrons, as happened in the last reaction. And similarly, we have our sodium moving in to help balance charge, and our nitrate moving in through our salt bridge to the right to help balance charge. You should pause video and think through, if it makes sense, why the salt bridge ions are going in the direction they're going, why the electrons are flowing through the circuit as they are, and make sure you understand the entire reaction. Determine the overall reaction for this cell. This time you're given a wet cell. It's a different wet cell. This time we have zinc ions, and we have a SHE electrode, standard hydrogen electrode, and notice that the voltage is 0.76. And you determine what the overall reaction is. So pause video and determine the overall reaction based on what you're seeing here. Turns out 2 hydrogen ions are gaining electrons in this case from the zinc. So it's the zinc that's getting oxidized, giving up its electrons to the hydrogen ions. Zinc becomes zinc ion. Hydrogen ions are gaining electrons and turning into hydrogen gas. So even though gas is produced, we still have hydrogen pumped in at 1 atmosphere bubble. We have a 1 molar solution on the right. We have a 1 molar solution of zinc nitrate on the left. Given that the SHE electrode cell potential is 0, what must be the potential for the zinc half reaction cell? Pause the video and try to determine the answer. It turns out the zinc half reaction is the only thing that's giving it an overall voltage of 0.76. So it has a positive potential of 0.76 when the zinc donates electrons. Here's a standard reduction potential from our book that shows lots of different ions accepting electrons, and it shows their various electromotive forces or voltages or cell potentials. Notice these are for just single half reactions, and they're all reductions as written. The things that are most likely to accept electrons and go to form what they do are shown up at the top because of the high positive voltage. Notice that hydrogen sets the base, the 0 level. Anything below this doesn't tend to want to go, if you will, because it has a negative voltage. So lead accepting 2 electrons is actually going to cost 0.13 volts. Bromine would love to gain 2 electrons and does so, releasing 1.09 volts. Our stronger oxidizing agents are up in the top right, and our stronger reducing agents, it turns out, are in the bottom right. And in fact, if we reverse any of these reactions, we'd get the opposite voltage. Determine which of the reactions below is spontaneous. Then draw a wet cell with electrodes, solutions, a salt bridge, and a voltmeter. Label the direction of flow of ions and electrons. Determine the overall voltage. So here are our 2 possible reactions. Either aluminum could react with lead ions to produce lead and aluminum ions, or the reverse. Lead ions could react with aluminum ions, producing aluminum metal and lead ions. To answer this question, you're going to want to look back at this table, and you're going to want to think about which reaction is most likely. Pause the video, try to determine the answer to this question. We need to start with the standard reduction potentials. We need to look for the reaction for aluminum gaining electrons or for lead gaining electrons. First, let's analyze the aluminum side of the equation. Aluminum could either lose electrons or gain electrons. The table only shows reduction potential, so the aluminum gaining 3 electrons is a negative 1.33 volts, and this is not favored. What would be the voltage of the reverse reaction? You're correct if you said it would be positive 1.66 volts, and remember, positive is favored spontaneously. So if this is all we knew, we'd say yes, aluminum would want to lose 3 electrons and have a 1.66 volt cell voltage. But we need to look at the other half reaction. Okay, well let's analyze. Lead could turn into lead ions, or lead ions could turn into lead. Look at the table and determine the voltage. Well, only reduction potentials are shown. Lead ions gaining 2 electrons has a negative 0.13 volts, so clearly the reverse reaction would have a positive 0.13 volts. Now, for the overall reaction, we're going to add the two half reactions. Which one overwhelms or which one would drive? Aluminum clearly wins in that battle, and the 1.66, you're going to want that to drive and the other to not. So if we put them together, so here's our answer. Aluminum donates its electrons to lead, and if we subtract the two voltages, the aluminum's negative overwhelms the lead's positive voltage to give an overall cell voltage of negative 1.35 volts. Now it turns out it doesn't matter whether the reaction occurs as shown unbalanced or if we actually balance it for the 2 aluminums and the 3 leads that would have to be required for our total of 6 electron change. Our cell voltage actually doesn't change even if we multiply up, which is something that will be explained shortly. To help understand this, here's a waterfall as an analogy. Water falling off a waterfall is kind of like the electrons dropping through a cell potential voltage, and this actually should be a positive 1.53 volts for a spontaneous drop down. So it turns out even if we have 1 atom of aluminum doing the reaction, or we have 2 atoms of doing the reaction, all that would change is the number of electrons falling off our waterfall. So it'd be like twice the volume of water, but we still have the same drop or cell potential whether it happens with 1 atom or 2 atoms. So let's work on sketching a wet cell for the reaction and label the movement of electrons. So here's our base reaction, and let's begin. Pause the video and try this on your own before advancing. Well, you're going to want to start with 2 beakers. And what do we need in our beakers? We need electrodes. So we need a solid aluminum electrode in one, and we need a solid lead electrode in the other. Well, what kind of solutions are in our beakers? For the aluminum electrode, we're going to need aluminum ions, but we can't bring those in alone. We need to bring nitrates in with it. So I've shown 3 nitrates. Now for our lead, we need lead ions, and of course we need nitrates. So we'd add a 1 molar lead nitrate solution. What else do we need? Well, we need a salt bridge. So our salt bridge will allow for, once the ions begin to flow, will allow to balance that charge. Let's add some ions to the salt bridge. We'll add sodium ions and nitrate ions, which tend to be non-reactive. What else do we need for our diagram? We need a voltmeter. So let's add wires coming out of the solution to our voltmeter and down, and then we'll be able to label things. So here's our overall reaction. Now try to determine what direction everything flows. Electrons, ions, what's the anode, what's the cathode. Take a moment, pause the video, and try to label things. To help a little bit, notice that it's the aluminum that's losing electrons, so electrons should flow from the aluminum to the lead, and this helps set everything up. Aluminum is going to be creating aluminum plus 3 ions in the beaker on the left. Well, with the addition of positive ions into the beaker on the left, sodiums are going to need to move away or run to the right. Nitrates are going to want to come in and help balance that charge. Similarly, lead ions are being lost from the beaker on the right, so a loss of positive means also that we need the sodium to come to the right. We need the nitrate to go away from the left. Which way are electrons flowing? From the aluminum to the lead, so from left to right as shown in this diagram. What's happening to the aluminum electrode? The aluminum electrode is losing mass, so that's our anode that's losing mass as it goes, and the lead is our cathode, it's gaining mass during the reaction. Electrons flow from left to right as shown. Aluminum ions are added to the left beaker. That causes sodium ions to need to flow to the right away from those buildup. Lead ions are lost from the right beaker. That means nitrate ions have to flow to the left through the salt bridge. Aluminum is the anode and decreases in mass. Lead is the cathode and increases in mass. That's a quick review of electrochemistry in wet cells, and we have a lot more to do later. Review as needed. Take care, gang. See you in class.